All right, so let's talk about real gas behavior this time. All right. Last time we said that in the limit of zero pressure, as pressure of the gas approaches zero, there's just one equation that describes all gases, and that's the ideal gas law, PV equals nRT. Okay. So if PV equals nRT, then PV divided by nRT must be equal to 1. Right? But that's, like I said, that's the limit as the pressure approaches zero. So the ideal gas law is an example of what's called a limiting law. Okay, and we said that typically under ordinary conditions around 1 atmosphere, you'll be in air and room temperature or 0 degrees Celsius, close to that, you'll be in air by about 1%. So let's see how we can handle deviations from ideal gas behavior. Well, okay, first of all, how can we tell if a gas is behaving ideally? Well, it should obey PV equals nRT, right? So you just measure pressure, volume, temperature, and number of moles. And based on that, you can calculate what's called the compressibility factor Z, which is just PV divided by nRT. If the gas is behaving ideally, what should that number be? Z should be equal to 1. So we can define compressibility factor as something that tells us whether or not your gas is behaving ideally. Okay, if it's equal to 1, it's ideal. Otherwise, Z would either be less than 1 or greater than 1. Can Z be negative? No, because pressure, volume, temperature, number of moles are all positive. So it's either less than 1, greater than 1, but it can't be negative. Okay? Now, compressibility factor is, why is it called a compressibility factor? Well, let's take a look at the formula for Z. It's PV divided by nRT. All right? Now, let's compare a real gas versus an ideal gas at the same pressure, temperature, and number of moles. Okay? So, Z for a real gas would be PV over nRT, and the V that we use here is the volume, the real volume of the gas. Z for an ideal gas would be equal to 1, which is pressure times the volume if it's ideal, right? Divided by nRT. All right. So what does it mean when Z real, the Z for our real gas is less than 1? Then let's compare these two. P over nRT for the same, okay, this is V real. Compare that with P over nRT V ideal. Okay, if this is this right hand side right here is equal to 1, right? If it's behaving ideally. At the same pressure and temperature as an ideal gas, your real gas Z is this one. Okay, so what does it mean if Z is less than 1? Then that means that the volume of your gas, the actual volume of your gas, your real gas volume, is less than what it would have been if it were behaving ideally. So it's smaller than what you might expect if your gas was behaving ideally. Okay? Similarly, if Z is greater than 1, then if this thing right here is greater than 1, then that means the volume of your real gas, the actual volume of your gas, is higher than what it would have been if it were behaving ideally. So why do you think it's called compressibility factor? What does the word compression conjure in your head? Shrinking, right? So Z is less than 1 would mean that the gas, it's as if the gas has shrunk. It's all in comparison to the ideal case. Okay? So in fact, in some cases, some authors prefer to use the word compression factor instead of compressibility factor, because it really has nothing to do with the ability of a gas to be compressed. It's just a comparison of the gas's volume to what it would have been if it were behaving ideally. Okay, so compression factor, I personally prefer that term instead of compressibility factor. But most textbooks use compressibility factor. Your textbook, Atkins, uses compression factor. So how do we explain ideal behavior? Okay. Well, let's see. PV equals nRT doesn't matter what gas you have, right? The nature of the gas. It doesn't matter what the structure of the molecules are. So why doesn't the nature of the gas matter? Well, the reason for that is if you're approaching zero pressure, you're looking at very large intermolecular distances. Okay? So at very low pressure, you're looking at very large intermolecular distances, and so interactions between the molecules are negligible. So it's as if they're all behaving independently of each other. It's as if there's nothing influencing them at all. Okay? So it's like saying, all right, if you've got people, if you imagine molecules as people, okay? You're in a big crowded room. You're in a big room, okay? If the people are so far away that you can't tell one from another, okay, there's minimal interaction between you two. Okay, so it doesn't matter if the person over there is ugly or beautiful, you can't tell. Okay, so the overall interaction would be about the same. Okay, but what happens when the pressure increases in the real case? So you start to see deviations from ideal behavior. So what if the room shrinks? So now you can see the person. So it now matters what kind of molecules you have. Okay, so there might be attractions and repulsions now that could factor into the behavior of the gas molecules. All right. So why can Z be less than 1? You would interpret that to mean that you must be dealing with a case that there are attractions among the molecules that would make the entire volume shrink compared to what it would be if it were ideal. So if the molecules just don't care about each other, you have the ideal volume. But if the volume appears to have shrunk, then that means there must be attractions, predominance of attractive forces that seems to be pulling those molecules in closer together. Okay, so if the average distances between molecules is such that the attractive forces are not negligible, then the entire system, the entire set of molecules that you have could end up occupying a smaller volume compared to the ideal case. So in this case, Z would be less than 1, and your volume would be less than ideal. How can Z be larger than 1? Well, this typically happens at very high pressures. So you're squeezing the molecules very close to each other, so it's getting too close for comfort, okay? And so repulsions start to set in. Remember, molecules are made up of what? Charged particles, right? You're trying to cram these charged particles as close to each other as possible. The nuclei will repel each other, the electrons will repel each other, right? So strong repulsive forces. So this tends to happen at very high pressures. You tend to get a Z larger than 1. So your volume would appear to be larger than the ideal volume. All right. So we can summarize the experimental behavior of a real gas and compare it with an ideal gas by plotting an isotherm. Okay, so a series of isotherms. An isotherm, what was an isotherm? Data points that correspond to the same temperature. So if you plot Z versus P, okay, for a given temperature, so these are typical isotherms you might encounter. What would be the isotherm for an ideal gas? If you were to plot Z versus pressure for an ideal gas, what would it be? What's Z for an ideal gas? 1, so it's just going to be flat, right? Z equals 1 everywhere. So I have here, so this dashed line right here is the ideal case. Typical isotherms you'll see is this. At very low pressure, what do you notice about the isotherms of real gases as pressure approaches 0? Your Z, whether it's real or ideal, would approach 1, right? But what happens? These are typical isotherms you'll notice. Some real gases would dip below 1, and then once you get to very high pressure, okay, the Z rises above 1. Okay, so that's one typical case you might encounter. Another typical case you would encounter is, this usually happens at very high temperatures, is that it will just rise above Z, above 1, and then just keep rising. Okay, so this tends to happen at higher temperature, and the dip tends to happen at lower temperature. Now, at even lower temperatures, it will dip, and then suddenly at a certain pressure, you can see a drastic drop in the value of Z, and then you have that rise back up to Z greater than 1 at very high pressures. Let's see what those mean. Okay. When you see this big drastic drop, you say that your gas is below what's called the critical temperature. Okay. And these are cases right here. The one on the left, those are cases where your gas, we say, is above a critical temperature. Okay. So these are isotherms above the critical temperature. Like I said, as pressure approaches 0, Z is equal to 1. Right? So at point J and K, what does it mean? Right? Z is less than 1, right? So what's that telling you about the behavior of the molecules? There are distances where what type of forces predominate? Attractions or repulsions? Attractions. Okay, at point L over here, what happens? Repulsions. C greater than 1. And notice T2 here is greater than T1. Like I said, the dip tends to occur at lower temperatures. As you go to much higher temperatures, eventually you may not see that dip. Okay. Now, what if you are below what we call a critical temperature? What happens is this drastic drop is actually an indication that your gas has liquefied. Okay? Remember, what's the density of a gas compared to a liquid? A liquid is much more dense compared to a gas, right? So if there's a big drop in the volume, density is mass over volume, right? A big shrinkage in a big shrinkage in the volume would make it more dense. So you're going from so your gas suddenly becomes much more dense. So what actually happened there is it turned into a liquid. All right. So what we have here for this particular isotherm at this particular temperature, this pressure where this happens is called the vapor pressure of your gas, of your substance. So you have a substance that's a liquid. Okay. So you can imagine you have a gas right there. You squeeze it. You get to a point, you reach a pressure where that gas starts turning into a liquid. So you'll have liquid in equilibrium with the gas at that temperature. The pressure where that happens is called the vapor pressure of your liquid. Okay? So you have liquid at points K and L over here. You have liquid and vapor at equilibrium. At point K, it's a gas. At beyond point L, it's a liquid. So point M actually represents a liquid here. Okay? So liquids become very hard to compress. In a liquid and a solid, the atoms and molecules are as close as possible. And further squeezing of those into a smaller volume would be very difficult to do. Here's another look at the behavior below the critical point. This one is a pressure versus volume isotherm. So you're plotting pressure versus molar volume. Okay, so over here, what happens when you have a large molar volume? That's low pressure, right? Low pressure down here, high pressure up there. So large molar volume. So at low pressure, Boyle's law, at a given temperature, the lower the pressure, the bigger the volume. What happens if you start raising the pressure of your gas? If you raise the pressure of your gas, what happens to the gas? How do you increase the pressure of the gas? You push harder on it, right? So you're squeezing it, so the volume is going to shrink. So the volume of the gas is going to shrink. Eventually, it reaches a pressure where you can keep pushing on it. The pressure will be maintained. The pressure will remain constant even as you're pushing it in, because as you're pushing it in, the gas changes to a liquid. Okay, so you start building more liquid. You're maintaining that pressure at that temperature. So this is what do you call that pressure there, where that happens? That's called the vapor pressure of the liquid. Now, eventually, if you squeeze it hard enough, far enough, all the gas turns into a liquid. Once you reach point K over here, what happens? Everything's a liquid, and it becomes very, very hard to shrink the liquid, right? So there's a drastic rise in pressure. You have to increase the pressure really high just to cause a small change in volume. We say liquids are highly incompressible. It's very hard to compress a liquid. Okay, so this is what you'll see. And if you were to compare this with an ideal isotherm, the ideal isotherm might look they're gonna okay. An ideal isotherm would behave something like maybe like that. Okay, remember, isotherm looks like that. So this you can see right here. Okay, for example, at pressure at point M. Okay, this might be the comparison of the ideal and the real. Your Z is less than 1 would mean that this curve is to the left of the ideal isotope. All right. This is the same one as before, huh? Looks like I've duplicated that slide. All right. So what's the effect of molecular structure on your isotherms, on the Z? Well, here's comparison of nitrogen, N2, CH4, H2, and carbon dioxide, all at the same temperature. So they have different isotherms. What do you notice at very low pressures? They all approach P, Z equals 1, right? But why does CO2 dip more than methane? And methane, CH4, dips more than N2. And then H2 doesn't even dip. This is at, I believe this is probably at 298 Kelvin. What do we know about carbon dioxide versus methane? Carbon dioxide, here's the Lewis structure. Whereas your methane is this one. Which one's a bigger molecule? Carbon dioxide. Okay. Hydrogens are very small atoms, right? And are these molecules polar or nonpolar? They're both nonpolar. So main interactions between these molecules would be London dispersion forces. So among carbon dioxide molecules, you're going to have stronger London dispersion forces compared to dispersion forces between methane molecules. So stronger attractive forces, you see a bigger dip than molecules that have weaker attractive forces. Okay. And you'll see H2 is the smallest of these nonpolar molecules. That doesn't even dip at room temperature. Okay. What's the effect of temperature? Like I said, at lower temperature it tends to dip more. Okay. So you say that deviation from ideal behavior is larger at lower temperature. At higher temperature, there is still deviation. At much higher, at very high temperatures, you also see deviation on the other side. Okay, Z tends to be larger than 1. So let's try to explain these deviations from ideal behavior. Let's talk about what's called the hard sphere model. Okay, molecules occupy a finite volume because of intermolecular repulsions. Remember, if molecules is made up of, let's just consider just noble gas atoms to make things simple. You have a nucleus that's positively charged, right? And it's surrounded by electrons. Now, if you have a neighboring molecule here, a neighboring atom, it's also going to be surrounded by electrons. You can only get these two molecules or two atoms as close as you can get them as close as possible, okay? But the closest you can get them is maybe around maybe 1 to 2 angstroms, around zero point 0.1 to zero point 0.2 nanometers, okay, typically. And in those cases, you have a bond, you have a covalent bond between them if they stick. Okay, that's as close as you can get them. What happens if you try to squeeze them further in? There's going to be very strong repulsions. So to a certain extent, then, because of that, in other words, because of those repulsions, you can say that you can imagine, if you can get them as close as possible, you can imagine that this would be the size of these molecules right there. So there's really, and a single molecule really, or a single atom doesn't really have a well-defined size, because the quantum theory tells us that that electron can be anywhere from the nucleus all the way to infinity, right? But so when we define sizes, we define it in terms of when it's as close as possible to another atom. Okay, what's the diameter? What's the volume occupied by that atom? So the size, then, the finite volume that we think of that's occupied by molecule has to do with the internuclear repulsions, actually intermolecular repulsions. Okay, so that's as close. When they're as close as possible, then you can use that to estimate the size of your molecules. So you can think of molecules then as just spheres. Okay, when the spheres are touching, then you say they can't go any further. Okay, any closer. So what that suggests then is that the volume that's available for molecules to move about is reduced. Okay, so if your molecule is in a box that's 1 liter, strictly speaking, it doesn't really have all that 1 liter to move around in, because part of that 1 liter box is occupied by the other molecule. Now, if you're dealing with very low pressures, there's very few other molecules in there, that error is negligible. But if it gets too crowded, then that error is not negligible. Okay? And so, because it's got less room to move about, okay, also, it's going to have more frequent collision with the wall. Okay? Why would that be? It's too crowded. Okay, so you're going to have more. You're going to end up with molecules colliding with the walls more frequently. That leads to higher pressure. Right? So let's see then what happens. Let's see how we can try to account for that mathematically. You can say pressure times the molar volume. V sub m is the molar volume here is just V over N, right? So PV, pressure times molar volume equals RT. That's your ideal gas equation, right? So we can rewrite our pressure is RT over V sub m. Well, because of this excluded volume, okay, because of the finite size of your molecules, you can say, all right, I'm going to introduce a correction for my molar volume, because my molecule can't really access all that volume around in the container. So I'm going to reduce that amount of volume that the molecule has access to. I'm going to introduce a correction factor for the molar volume. So we say that the volume that's available to the molecule is less, right? So I'm going to subtract from molar volume. I'm going to subtract this parameter, which I'm going to introduce. This is called the excluded volume parameter. So what happens then if you're dividing by a smaller volume now? Your effective volume is smaller. You're dividing by a smaller volume, so the pressure of your gas would now be higher than the ideal volume. Smaller denominator, the whole thing becomes bigger. So this is how you would explain why the pressure of your gas would be higher than ideal. Okay, so you say the pressure of your gas would be higher than ideal, because when it's too crowded in there, that there's a significant deviation from ideal behavior because it's too crowded. When it's too crowded, it's the repulsion set in. Okay. Now let's take a look at what it means if the pressure is higher than ideal. Well, here's the pressure of a gas, okay, the actual pressure, divided by the ideal pressure. Well, what's pressure? What's the ideal pressure? It's just nRT over whatever the volume is, right? But we can rearrange this right here, the actual pressure over the ideal pressure. Right, that's that one, right? We can rearrange that. That's just PV over nRT. So that's just Z. So another way to look at Z, instead of thinking of it in terms of compression, think of it in terms of how the pressure of the gas compares with the pressure that it would have if it were behaving ideally. So Z greater than 1 means for the same volume, an ideal gas would have a lower pressure than your actual gas. So your real gas pressure is higher than what the ideal pressure would have been for that particular volume at that temperature. So that explains Z greater than 1. Okay, so repulsions, okay, lead to molecules having finite volume. And because of these repulsions, okay, within that same volume, a real gas is going to exert a greater pressure than an ideal gas. And so that's one way of looking at the compression factor. Now, how do we account for corrections for attractions? Well, okay, so our hard sphere model, we say, is okay, pressure equals RT over Vm minus B. What is this B right here? That's your excluded volume correction, right? Due to repulsions. Okay. Now, what happens if there are attractions? You have to take into account what's the effect of attractions on the pressure. Well, pressure is due to collisions with the wall, right? So if you have a molecule, if you have molecules and you have a wall right here, collisions between the molecules and the wall imparts a force on the wall. Okay, force divided by area gives you the pressure. But imagine right here now you've got a molecule approaching the wall, okay, and you got other molecules nearby that's going to attract that molecule. What's going to happen? Is that molecule going to speed up or slow down? If that molecule feels a net attraction to other molecules as it's approaching the wall, will that molecule speed up or slow down? If it slows down, what happens? It's going to impart less force on the wall. So the effective pressure that your gas molecules will exert on the wall will be less because of the attractive forces that are pulling back on the molecules as they approach the wall. Okay, so you introduce another correction then. Because of repulsions, you can say the effective pressure will be less. I mean, because of attractions. So you subtract from your total pressure right here. So here's your hard sphere expression for pressure, RT over molar volume minus B. Okay, that's your hard sphere. This accounts for repulsion, this B right here. Now to account for attractions, you subtract correction you made to lower the effective pressure. What affects this? What determines these attractive forces? Well, it depends on what molecules you have. What's the nature of the molecule? So it's going to be, and it depends on the concentration. How many other molecules are affecting this molecule, right? So it depends on how many other molecules are affecting each molecule. And it also depends on how many molecules are affected. So your correction would be proportional to the square of the concentration. So minus A times N over V, and then squared. Okay, it depends on the square of the concentration because it depends on how many molecules are affected. So that's concentration. And it depends on how many molecules are affecting the molecules that are affected. So that's why you have that squared term right there. So this is your van der Waals equation. So you can rewrite this as P equals RT over molar volume minus B minus A. But N over V is just 1 over molar volume. Okay, so 1 over V sub M squared. Right, so this equation right here that tries to account for attractive and repulsive forces, okay, is known as the van der Waals equation. So this is a better equation to use, okay, under conditions where ideal behavior is not observed. Okay? So this A right here depends on the nature of the molecules. Molecules that attract more strongly, you expect to have a bigger correction, so you have a bigger value for A if you have molecules that attract more strongly. And B right here, what does this B right here stand for? That's called the excluded volume. Okay, that accounts for repulsions when the molecules get way too close to each other. Okay, so that depends on the size of the molecule. So this gives you an indication. The van der Waals parameter B gives you an indication of the size of the molecule. Size meaning how close can they get to each other, and that would determine the size. Okay, before repulsion sets in. So A here is a measure of the attractions, attractive forces. Okay. So here's some values, experimental values for the van der Waals parameter. Note that the unit for B is excluded volume, so the unit for it is liters per mole. Okay, so here's the value for O2 versus the value for H2. Can you explain why the value for O2 is larger than the value for H2? O2 is a much larger molecule than H2. So the excluded volume for O2 will be larger. Okay? How about A? It accounts for attractive forces, intermolecular forces of attraction, and the unit for A is liters per mole squared. Let's see where that comes from. Remember our pressure was RT over molar volume minus B minus A times 1 over molar volume squared, right? What should be the unit for A? The unit for this whole thing must be a pressure unit, right? Since this is a pressure is equal to a pressure term, so this must have a pressure unit. So this whole thing must have a unit of pressure. You can make it bar or atmosphere. So if it's bar, okay, and 1 over molar volume, what's the unit for 1 over molar volume? Squared. Molar volume is, so that's just N over V, right? Moles per liter. So that's moles per liter squared. Whatever the unit for A is, that times moles per liter squared must be a pressure unit. So that would have to be a bar unit. Right? So what would be your unit for A then? It's going to be bar times the reciprocal of moles per liter, right? Which is going to be liter squared per mole squared. So that's the unit for A. Okay? So bar liter squared per mole squared. Here's a comparison of values of the van der Waals parameter A. It's 5.58184 C2H6. It's 2.3026 for CH4. Why is it bigger for C2H6? What are we comparing here? Intermolecular forces. Both of these are nonpolar molecules. So what's the only type of intermolecular interactions that they have? What intermolecular force? It's not dipole-dipole. There's no hydrogen bonding. What do you call the interactions between nonpolar molecules? London dispersion forces. And when is London dispersion forces stronger? When you have larger molecules, okay? Because if you have a larger molecule, there's greater likelihood of polarization, temporary polarization. So temporary formation of dipoles, because these electrons are moving around your molecule, okay? At any instant, you can have what we call instantaneous dipoles. And it's more likely to happen the larger the molecule is. You say the molecule is more polarizable. So between a pair of C2H6 molecules, you're going to have stronger interactions than between a pair of CH4 molecules. How about H2O versus H2S? Which one do you think is going to have a larger A value? Which one is larger? Going down a periodic table, oxygen versus sulfur. What happens to the signs? This one would have a larger size, right? So you would expect this to have a larger B value. Remember, our B value depends on size, right? So do you expect, which one would you expect to have a larger A value? You might expect H2S to have a larger A value because it's larger. It would have stronger London dispersion forces. In fact, this is an anomaly because there is another type of interactive force, intermolecular force among water molecules that makes them attract each other more strongly. And what is that? Hydrogen bonding. Okay, because of hydrogen bonding, this actually has a larger A because of hydrogen bonding. Hydrogen bonding interactions. Okay, so you can look these values up. There's a table in your book that has these. Okay, let's talk about critical points. Critical point is a temperature, critical temperature first. Okay, so temperature above which you cannot liquefy gas. Remember when we plot that Z versus P, we have that, this is ideal as Z equals 1, right? And you have a dip, right, below Z equals 1. And then at a certain pressure, you see that big drastic drop in the volume. That's liquefaction. If that doesn't happen, you say you're above the critical point. So what happens is as you raise the temperature, so at a higher temperature, you might get something like this. At an even higher temperature, you might get something like this. So that drastic drop becomes less and less pronounced as you go to higher temperature. Eventually, you get to what's called a critical point where you have what's called, in math, we call that an inflection point. Okay, so at that particular temperature, okay, so all of these drastic drops are going to get smaller and smaller and smaller until you reach this point right here, which we call the critical point. So that's an inflection point in the curve. And the temperature where that happens, that's called the critical temperature. So you say below that critical temperature, your gas can be liquefied without changing its temperature. All you have to do is squeeze the gas, increase the pressure without cooling it. Okay, maintaining the temperature, you can liquefy the gas. But above that critical temperature, you cannot liquefy the gas. And experimentally determined values of critical, the pressure where this happens, okay, and the temperature where this happens, that refers to what you call the critical point. So where that inflection point occurs is your critical point, and that has been determined experimentally for a lot of substances, and you can look those up, okay? And you can use those to calculate van der Waals parameters. So let's illustrate. Here's I think I've got a real nice animation here. That this is not an animation anymore because I have this. Yeah. Okay. So like I said, this is a PV isotherm, right? So this might be the isotherm down here at a low temperature. So what happens here? You're squeezing the gas, you're raising its pressure, right? Pressure goes up gradually. Eventually, it reaches a point where further squeezing will not cause the pressure to change. Instead of the pressure changing, the volume just drastically drops until everything's turned into a liquid. And what happens? It takes a very large amount of pressure just to get a small change in the volume of the liquid. Okay, so this point right here is the molar volume of the gas, and this point right here is the molar volume of the liquid. Okay. Now, what happens at a higher temperature? This happens, okay, liquefaction occurs at a much higher pressure. Okay. So you're going to need to raise the pressure a little bit more before you can get it to liquefy. So this is the molar volume of the gas. This is the molar volume of the liquid. So those things can be measured. At an even higher temperature, that trend is going to continue. That drastic change is going to get smaller and smaller until you reach this point right here. That's called your critical point. That's an inflection point. So what's the value of the derivative there? At the inflection point, dp dv is going to be equal to 0, right? And that's also the point where your curve changes from concave downward to concave upward. So at the inflection point, what's the other condition that's satisfied? Second derivative of P with respect to V is equal to 0 at the critical temperature, at the critical point. Okay? So if you apply this to the van der Waals equation, okay, and you know what your critical point is, you can calculate the van der Waals parameters. So you start with the van der Waals equation, take the derivative of P with respect to V sub m, the molar volume, take the second derivative, set those first and second derivatives equal to 0, and what you get is you'll find that you can solve for A. The van der Waals parameter A would just be 27 times R times Tc, that's the critical temperature. So squared divided by 64 times the critical pressure. So you can derive that. And the van der Waals parameter B is just R times the critical temperature over 8 times the critical pressure. So if you have a table of critical points, you can determine the van der Waals parameters from those. Okay. Now, what happens below the critical temperature if we were to actually plot the van der Waals equation? You'll find this is the van der Waals equation that you get. And if you plot it, this is the curve that you get below the critical temperature. Okay, you see a loop. Instead of what do we expect the gas to do below the critical point, critical temperature? You see that this is what we would have expected, right? But instead, if you were to plot the van der Waals equation, you get that loop right there. Right, so that's what you'll see if you were to plot it. And the van der Waals equation really is just a qualitative equation. It's not perfect. It's not as accurate as can be, but it's a little better than the ideal gas equation. You can have more accurate equations using. There are other equations that are more accurate than the van der Waals equation. The Redlich-Kwong in particular, and Virial equations are just purely based on empirical data. So. They're the ones that are more useful if you want to actually calculate numbers for your experimental predictions. Okay, so let's talk about Virial equations. A Virial equation is an equation. It's an empirical equation. What do we mean by empirical? It's just based on experimental data. Okay, so. It's just we can think of it as just a brute force attempt to fit the experimental data to an equation. And the best equation to use to fit data is just a polynomial. Just add as many powers as you can pretty much fit any equation, any data to an equation. So a Virial equation expresses the compression factor Z as a polynomial in P or as a polynomial in 1 over Vm. So for each isotherm. Okay, so compression factor can be written as 1 plus a constant times 1 over molar volume plus another constant C times 1 over molar volume squared plus another constant times 1 over molar volume cubed and so on. Or you can say Z is equal to 1 plus B prime times the pressure, B prime being a constant, okay, plus C prime, that's another constant, times P squared plus D prime times times p cubed and so on. Now B, C, B and C and D and so on, these are called your virial coefficients. And B prime are also called and C prime, those are also called virial coefficients. Okay, so the coefficients in this expansion are called virial coefficients. What would be the unit for B? What would be the unit for B? What's the unit for Z? Compression factor. Z is PV over nRT. Right? So what's the unit for Z? It's unitless, right? 1 is unitless. So what's the unit for B then? B times 1 over molar volume must be unitless. So what's the unit for 1 over molar volume? Moles per liter, right? Right? It's a concentration unit. So what's the unit for B? B has a unit of liter per mole. So B has a molar volume unit, moles, liters per mole. What about the unit for B prime? If P is in atmosphere, what would be the unit for B prime? If your pressure is in atmosphere, then the unit for B prime will be reciprocal atmosphere, or a reciprocal pressure unit. Okay. So B and B prime are called the second virial coefficients. C and C prime are called the third virial coefficients. And these virial coefficients depend on the temperature. So it depends on what particular isotherm you're dealing with. Okay. And so generally you would see these values tabulated as a function of temperature. So B, then you might find the equation for B for a particular gas expressed as a polynomial in terms of T. Okay. Now, as P approaches 0, what do you notice about these equations? B over Vm is going to be equal to B prime times P, right? What happens? Let's look at some approximations we can make. If you're going to approach P equals 0, then if you truncate your equation to these two terms right here, okay? Remember, as P approaches 0, Z will approach 1, right? So these two numbers are going to be more or less the same. Okay, so B over Vm will be approximately equal to B prime P. So you can relate B and B prime. And so B is equal to B prime times P times molar volume. Right? Can you see that? All I did here was move the molar volume to the other side. And pressure times molar volume, okay, over RT is just equal to Z, right? Molar volume is B over N. So molar volume is B over N. So that's just equal to Z. So this thing right here, P times molar volume, is just ZRT. Okay? So B is just going to be equal to B prime RT, since Z is going to be approaching 1, right? So that's a relationship between B and B prime. So if you can look up the value for B, you can solve for B prime. If you can look up the value for B prime, you can solve for B. This is how the two are related. Okay. So how are these determined? Experimentally, what you do is you measure your P and your molar volume at a given temperature. Okay? And so what you can do is you can tabulate for a series of pressures or a series of molar volumes. You can tabulate Z minus 1, P, and P squared. Okay? And then you do a linear regression. Okay? So remember, we have Z is equal to 1 plus B prime P plus C prime P squared and so on, right? So you can move this z over to the other side. So z minus 1 is b prime p plus c prime p squared. And this is just a linear regression problem. Your independent variables are p and p squared. So you have 2 columns, okay, of p and p squared, and a column of z minus 1 would be your dependent variable. And in this case, when you do your regression, you force your y-intercept to 0. So the coefficient of p will be b prime, and the coefficient of p squared would be c prime. Same one. Same thing. If you measure 1 over molar volume instead, you can determine b and c. Right? And we're going to look at an example of this in the lab for one of our activities. We're going to determine the virial coefficients. Okay. What time are we supposed to end? And that's about 3 minutes from now. Okay, so let's just finish this up next time.